think the recording started. So we'll start now. Um, it's been we had a very long gap between the two sessions. This is the second class on antennas and radiating systems, and the previous class we covered introduction and radiation fields of elemental dipoles. So we looked at the elemental electric dipole and the elemental magnetic dipoles. We saw the auxiliary potentials and the far field equations and stuff. So, and in this class, we'll start with antenna patterns and antenna parameters. This is the reference book which I'm using for this course. We discussed in details the class logistics in the previous class. I've shared this book. If you haven't still got it, please put a message. Uh, these are the other books I will recommend if you're going through this course for the first time. You can also use this antenna theory by C.A. Balanis. It's a very good book. Everything is written in much details. If you are not able to follow this textbook, use this one. In the previous class, we looked at the introduction and the elemental dipoles. We went through quite a lot of topics. We looked at the auxiliary potentials, the electric field, the relationship between electric field and magnetic field, and how we'll solve them. This was the crux where we have to determine the auxiliary potential A and from the current from the current density J, and then find the magnetic field from the auxiliary potential A, and then electric field from the magnetic field. So this is how we were solving for the electric and magnetic fields from the sources, and then we so by using the three steps, we calculated the electric and magnetic field for the Hertzian dipole and the elemental magnetic dipoles. So we did a lot of math, but I hope you got time to go through these steps. Uh, it's just a lot of writing and multiplying and dividing of different Greek and Latin letters, but it's pretty straightforward if you like try to write it. So and also some part of it is like based on your previous knowledge of electromagnetic theory. So if you have done that course, you'll be pretty much comfortable with the notations which we're following in this course. In this class, we'll discuss antenna patterns and antenna parameters. First we'll look at what are these patterns, and then we'll quantify some properties from those patterns as parameters. And for the antenna design, these are the terms which we use to specify our requirements. For example, if you are one of those people who design antennas and somebody is giving you a task, so they will ask you to design a certain type of antenna so that it can give a certain type of pattern and um, meet these criterias and they'll specify you the parameters. For example, how much gain for the antenna would be, how the pattern would look like. These things will become clear when we go through the material which we'll look at now. So, antenna problems, we primarily are interested in the far field zones. So in the previous class also, we derived the expression for electric field and the magnetic field, and based on the expression, we divided it into the near field, midfield, and far field. So, based on how the electric field radiates at a certain distance, we divided into different zones. For example, we saw there were terms of the form 1 by r, 1 by r square, 1 by r cube, and based on which term is dominant in which region, we divided those fields. And so most of the measurements or most of the working of the antennas, they are like we consider them in far field, and we study that. There are certain areas in which near field is also is of more importance. For example, wireless power transfer, and some cases of biomedical applications where near field things are more dominant. But for most devices, for example, your mobile phones or the antennas in your laptops, all base stations, all these places, the zone in which we are working is the far field zone. So, and the far field zones, the antenna, how the antenna radiates are like this region is this the region where we are focused now is called the radiation fields. And it is known that no physical antenna can radiate uniformly in all directions in space. So there's some exists something called an omnidirectional antenna, but that is a hypothetical situation where it radiates equally in all directions. But physically, it is not possible. We do not have omnidirectional antennas. We have isotropic antennas, some directional antenna. So there are different forms of radiation patterns which we'll look at, but we don't have antennas which radiate uniformly all directions. And since they do not radiate uniformly in all directions, it is very important that we know how it is radiating in different direction, so that we can modify our design. For example, if you want two devices to communicate and the antennas don't radiate equally in all directions, you'll want them to radiate the performance to be better, or you'll want them to radiate in the direction in which the two antennas are facing each other, or so that they can communicate better. So we'll look at we'll discuss that now. So there is something called radiation pattern. It is a graph that describes the relative far field zone strength versus the direction at a fixed distance from the antenna. Okay, or it is simply called the antenna pattern. So maybe I'll try drawing something if this works out. So for example, if you have an antenna, it this is like symbolic representation of an antenna, and if it is radiating, so it might radiate in different ways. For example, if it is radiating like this is something like we have higher field strength in this direction, and there is a some radiation in this direction. And so by these are this is the strength of the electric field. So in this direction we have higher strength, this direction we have lower strength, this in these directions we have more lower strength. So therefore, if you have two antennas and if you want them to be to communicate, you'll try that uh, both these antennas, they have the higher radiation strength in the direction in which both of them can communicate. So to ensure that we must know how the antenna is radiating. And the radiation pattern is something, if you, for example, if you have designed this antenna, and if you try to see how the electric field is radiating in all directions, so you can what you can do is you can measure the field strength in in different directions all around the antenna in different planes. And what you can do is plot their values around the antenna. So, for example, over here, this was the strength you received. 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 So, and then what you can do is you can join them, and you'll find that the antenna radiates. The radiation pattern looks something like this. So we know that uh, the antenna is at a certain angle, it is radiating its main radiation of direction is at a certain angle from the antenna. So when you position now your antenna, you can position the antenna in a way so that the other antenna, the this main the direction in which it is radiating higher radiation is there, you can focus that to the receiving device. So in general, an antenna pattern is a three-dimensional varying in three-dimensional. It is varying with both theta and phi. So if you are taking a coordinate system, so you're if and you have an antenna over here, so this pattern is a three-dimensional structure. So it will it the antenna radiates in all directions, right? I mean to say that in some directions it will radiate more, in some directions it will radiate less. But in the 3D space, it will you will have some radiation in all directions. So at a certain distance, if you might say, for example, if you take some r distance, at r distance, what you can do is plot the field values around the antenna, and then you will get a pattern of how much the power is there in that direction. And when if you plot that, you will get a 3D structure, 3D three-dimensional plot, which shows how much power is there in each direction. Uh, but obviously, visualizing a 3D plot is difficult, especially on pen and paper. Like and to present your work as well, how the antenna is radiating. What we do is we take slices of this 3D pattern, and for different values of theta or phi, and based on that we see how the pattern is. So if you are given different cross sections of the 3D radiation pattern, you'll be able to get an idea of how the antenna is radiating. Okay, so in the next example, we'll see how the Hertzian dipole radiates. So there's something called the E-plane pattern, and this E-plane pattern is for various values of theta for constant phi. So we have chosen a phi value, and then we are plotting the value for different values of theta. So we are varying theta from 0 to 180 degrees in either direction. Yeah, 0 to is 3. Yeah, 0 to 180 degrees, and for different values of theta, we are receiving different amount of power, and we are keeping the phi fixed, and that gives you the E plane pattern. And for the H plane pattern, if you choose theta equal to pi by 2, we're choosing theta equal to pi by 2, and for a fixed value of theta, we are varying the phi from 0 to 360, and we are getting one radiation pattern over here. So this is the H plane pattern. So basically, we have chosen two planes in which we're primarily looking at. But to get a complete idea, you can also do a 3D plot using MATLAB, or if you're simulating structures in HFSS or CST, it gives you the 3D design. But if you're writing a paper, you obviously you give cross sections of the radiation pattern. So by using these two sections, we can get an idea of how the radiation pattern would look like. So it would, if I try to draw it in a 3D plot like this, it will look something like this. So if you are getting an idea, so this is the outside. It will look like an apple sort of thing. If you get an idea, and this is the axis. Okay, I did not draw the axis properly, but this is something it would look like. It would look like an apple. So there is some depression in the center, and then it bulges outside, or like a donut, if you imagine. So this is how, and if you, so for example, if you take the cross section of a donut, If you slice it like this, you will see two circles, and if you slice the donut from the top, you will see a circle, and with the small circle inside. So this is something we have drawn over here. So in the next slide, we'll see how we uh, get these patterns. But I'll stop here and take questions if you have. Okay, just to check, I'm still audible, right?
Yes, sir.
Okay, thank you.
I have
My
a
internet,
question.
yes.
Uh, the radiation pattern of different types of antennas are different.
Yes. Like there could be two antennas who can have the same similar radiation pattern, but in general, yes. If you change, like you can most many antennas, they have different radiation patterns. Yes.
The radiation pattern only gives the far zone field strength, or it also gives the sir near field strength.
So the radiation patterns are plotted for the far field. Like when we plot these patterns, we do some approximation of the electric field strength at a certain distance. If you remember, we had the electric field proportional to some function of 1 by r, 1 by r square, 1 by r cube. There were terms like these, right? So what we in so when we start plotting the radiation pattern, we ignore these terms. So once you have ignored these terms, we are plotting them in the far field. If you want to plot a radiation pattern in the near field, you'll have to consider the full expression, so that you're plotting the correct values of the field in the near field. You can obviously do a near field radiation pattern plot, but you'll have to ensure that you're using the correct expressions.
Okay. Okay. Thank you, sir.
I was going to say my internet is a little bit wonky, so if I get disconnected, please let me know. Okay, so if there are no further questions, we'll proceed to see how to plot the radiation pattern of a Hudson dipole, which we are seeing them right now. Okay, so this is one of the examples from the textbook where we have been instructed to plot an E plane and the H plane radiation patterns of a Hudson dipole. We in the last class we had discussed the Hudson dipole, the elemental electric dipole, where we had a small conductor and we plotted the electric field and the magnetic field of at a certain distance from the this particular dipole, and upon the derivation. So if you remember, we had the value of J, and from J we got the value of A, and from A we got the value of H, and from H we got the value of E. So this is how we went, and then so at the end we had the value of electric and magnetic fields at the distance, and there were these expressions over here, the H phi and E theta. So we have the electric field and magnetic field expressions in the far field. You must remember, over here we had more terms, like they were higher order terms, which we have ignored because these are the far field expressions. So since E theta and H phi in the far field far zones are proportional to each other, we need only consider the normalized magnitude of E theta. uh, so these are proportional to each other in the sense there is only this term which is different in both the impedance of free space is the only difference in between these two expressions. Rest of the things are same, so we need not consider. We can just only take the electric field values what we mean to say. So we have the E theta expression. Now for the E plane pattern at a given r, so we have this expression, right? So we have this r over here. So for a certain r, so we're making the r like we're fixing the r. E theta is independent of phi. So you can see there is no expression of phi in the electric field expression over here. There is no phi, so it's independent of phi. And like and the normalized magnitude of E theta is just sine theta. So all these terms in front of this, if you're fixing the value of R as well, everything is a constant for this, and there is no phi variation. So the normalized electric field will just be mod of sine theta. So we have got the value of mod of sine theta, and so the E plane pattern function of the Hertzian uh, dipole is given in this figure over here. So if you plot the sine theta value, yeah. So if you plot sine theta for different, if you yeah, yes. So yeah, basically this sine theta is a locus of concentric circles, and if you plot this for different values of phi, this is what you would end up. So you probably have to write a MATLAB code to do this. It's very difficult to like visualize this, but we'll just take for the word of the what is written in the textbook that this, if you plot the sine theta for various values of phi, this is something would we will end up. Maybe I'll try to write a sample code and share with the class so how this works out. But this is how the sine theta would look like. And similarly, for the H-plane pattern, if you for any given r, and for theta equal to pi by 2, okay, yeah, for theta equal to pi by 2, this if you put pi by 2 in this sine theta over here, this would just become a constant, and yeah, sine theta will become 1, and if you plot this, this will become a circle. Okay, so this is all this is happening in the cylindrical coordinate system. So that's why it's difficult to imagine. So in the Cartesian coordinate, the sine theta looks something like this, but in the cylindrical coordinate, it probably becomes like this. And in Cartesian coordinate, this constant is like this, but in the cylindrical coordinate, this becomes a circle. So this is something which is happening if you can like if you can relate, but you can also write MATLAB codes and stuff, so which will make your like life easier. So at for if you solve more examples, you'll end up with different functions of these trigonometric functions, sine theta, cos theta, their multiplication, and you probably won't be able to imagine how that expression looks like until you plot it. So so there is one task. Even if you've got the answer, you can't visualize it by looking at the expression. You'll have to plot and see how the pattern looks like. But over here, we can get some idea that a sine converts to something like this, and constant converts to something like this in the okay. This is the spherical coordinate system, not the cylindrical. So this is how we have got the E-plane and H-plane pattern. It was fairly simple. We have the expression for the electric field. We normalize it, so everything, all the constants, they are like gone. The R is now fixed, and so we end up with all the trigonometric functions on theta and phi, and we just plot that, and we'll get the E-plane and H-plane patterns. So I'll stop here, like I'll pause here and let you read the text and the see the figures, and take questions if you have, and on like on this example. Okay, I was on mute. So I saw some messages regarding people not being able to join, but I see their names now in the attendees list. So I guess the link worked. Um, okay, so we'll proceed now. Okay, so we'll come to this. Don't be stressed with these figures if you're seeing them for the first time. The so the when we started, we said that the radiation patterns for different antennas, like the antenna does not radiate equally in all directions, and different antennas have different radiation patterns. And the radiation, and so now we're saying that radiation patterns of practical antennas are very are usually more complicated, like the example which we saw in the previous slide, where it looked like one circle and then two circles. So this is true for some antennas. If you're making a simple patch antenna, you'll probably get something like this in one of the directions, and this is what you want to achieve. So this is an example of an I this what is this Teams? There is some notification from Teams on. Okay, never mind. So yeah, so this is an example of an isotropic antenna. So isotropic radiation pattern. So where in one of the planes it radiates equally. An omnidirectional one radiates equally in all direction, and isotropic antenna radiates equally in at least one plane. Okay, so this an isotropic antenna. This Hudson dipole is an example of isotropic antenna. Omnidirectional antennas do not exist, and then there are some antennas, like some more like most antennas that we design them for higher directivity. We'll discuss what directivity is, but from the term you can get a sense that we want the antennas to be more directive. For example, if I am this is me over here, and if I want to talk to my friend over here, instead of and I'm using some device, and instead of like and he's also using some device, and I will want all the power that my device intends to transmit should be transmitted directly to him, and so that he can receive. And instead of radiating the power equally in all directions, it will be better if all the power is directed towards his device. And I will also want that whatever device he's using to uh, be more directed towards where I am standing instead of receiving in all directions. So this could be one scenario. So where we'll prefer a more directive antenna whose radiation pattern will look something like this over here in figure 11.4a. And there could also be cases, for example, if this is me and I want to talk to a bunch of different people who are all around me, and I want to send them data, send them some information simultaneously, or I want to talk to all of them. So in this case, I will prefer an omnidirectional pattern. But since omnidirectional antennas do not exist, I will want an isotropic antenna so that it radiates power equally in all directions. And they could either use a device which is directed towards me, or if they also prefer to talk to their other friends, they would also prefer an isotropic design, isotropic pattern for their antenna, so that all of us can talk to each other using our devices. So I hope you follow, like in different scenarios we prefer antennas which have different radiation patterns. And there could be other cases as well where where like I for sure know that I have only two friends and I want to talk to them only. So in this case, I will prefer an antenna which has my device should have an antenna whose radiation pattern could be like this. It has uh, it radiates power in high power in directions only, and so that I'm able to transmit more power in those two directions. And they could have a device as well. So we are just only three friends, so we will have all have devices which has and antennas whose patterns look something like this. So we are radiating high power in only two directions, and in the rest directions we do not radiate much power. I hope you can follow. So based on the needs, what you can do is you can tune your antenna, design your antenna to meet a certain type of pattern that you want. And so we started from saying that radiation patterns of practical antennas are usually more complicated, and this complication is usually introduced by the manufacturer who wants a certain kind of design. And a typical H-plane pattern might look like one illustrated in 11.4a. So this is the pattern which we're talking about. This is a very design of a very practical antenna that we see in many places. For example, base stations and stuff. And this is plotted in the polar coordinates. So this is this is the phi direction, and we have this one place we'll have the theta and then r. So you understand the polar coordinates. So it generally has a major maximum and several minor maxima. So this is the major maximum over here, where we have the maximum power, and we refer it as the main lobe, and we call these at the side lobes. So we'll encounter these terms again. Um, so these small lobes, you can see the small lobes, where as the name says, these are the small lobes, and this is the main lobe or the major lobe, and this is the major maximum, and then we have the smaller maximum. And based on applications, we might want one major lobe, two major lobes. This was the case of one major lobe, two major lobes. Over here, we could have an isotropic, or based on number of people who want to receive the signal, that many number of lobes. But usually we have only one major lobe and several minor lobes. And the region of the maximum radiation between the first null points, the first null points are over here. So you see this line over here. This is the place where the power becomes zero, along like too closer towards zero. Like we have the minima over there. So where we so the minimas are known as the nulls. Nulls are known as the minimas. So where we find the first minima or the first nulls are it is so between those two first nulls is the main beam. So over here, this over here in this direction, this we have the first minima, we have the second minima, or the first and the second nulls, and between the these two nulls, we have the main beam, and the regions of the minor maxima are called the side lobes. So if now we have nulls over here as well, right? So between these nulls, we what we have is called the side lobes, and this is the main beam or the main lobe or the major lobe, whatever term you want to refer to it. So this is how we like these are the names which like we are used to. Uh, we'll come to this figure in the next slide. So this is for a Hertzian dipole, and this is for a more realistic dipole. This is how the radiation pattern would look like. So I'll again pause over here, let you see the slide if you have any questions, or else we'll move to the next slide. Okay, so we're going slowly about this. If you do not follow, don't like you can put a message in the chat or you can ask as well. Okay, so these are the same figures over here. We have discussed this figure, but now an important issue is that it's very difficult to study this figure. It's although it's very easy to visualize how the antenna is radiating. For example, if this is probably how the Hertzian dipole, sorry, not Hertzian, the realistic dipole looks like. So this is the dipole over here, and oh, sorry, I've made it in the wrong direction. Here. This is in this direction. The dipole is, yeah, where the bigger uh, bulbs are put. So this is how the dipole is lying, and then around the dipole you have this radiation pattern happening. But it's although it's easy to visualize how the radiation pattern is around the antenna, but it's very difficult to read the plot. So what we do is we convert it into the Cartesian coordinates. Like we plot it like this. We have phi over here instead of phi moving around like this. We have spread out the phi, and now we have plotted the magnitude for different values of phi. So this small lobe over here, this particular small lobe becomes this thing. This major lobe becomes this thing. So now it's much easier to visualize how like how to like it's much easier to read the plot, but it's difficult now to visualize how the radiation pattern would look like. So we constantly switch back and forth between these plots to study and visualize. So that's what the text will say. Sometimes it is convenient to plot patterns in the rectangular coordinates. So this 11,4a becomes 11,4b in the rectangular coordinates. This is 11,4b. And since the field intensities in the main beam and the side lobe directions may differ by many orders of magnitude, the antenna patterns are frequently plotted in logarithmic scale. So over here it is fine, but it might happen in the Cartesian coordinate that the main beam is very high and the minor lobes are very small. So again, the problem would be like if this magnitude is very small and this magnitude is very high, you will not be able to read or like visual study the side lobes. So what we do is we take the logarithmic scale. So this solves the problem because uh, this particular plot would convert to something like this because uh, yeah, so this is 0 dB, this is minus 3 dB over here, this is minus 8.2 dB. So it solves the problem of very high varying magnitudes. It brings them down to a more realistic scale, and now it's easier to understand, but easier to read the plot. So this is the polar plot, and these are the rectangular plots. The rectangular plot uh, in normal magnitudes, and in this is in the and this is in the logarithmic scale. So this is all we were supposed to talk about antenna patterns. Now we'll look at antenna parameters. So uh, the things you would have realized while looking at the patterns is that we are just getting an idea of how the antenna is radiating in the space. In which direction we have the low and we can figure out in which direction we have the main lobe, or where it is we have where we have the minor lobes, but we have not yet quantified anything like how wide is the main beam, how high are the side lobes, how much power is being lost in the side lobes, how directive is how much gain are you getting, the efficiency so these things, the quantified values we have not yet looked at. So those things are the antenna parameters which we'll look at now. So before we start that, I'll again pause here, and if you have questions on this, on the antenna patterns, the radiation pattern, um, on the polar coordinate, on the rectangular coordinates, we can discuss that. Else we'll move. So pause here. Let you absorb what we discussed.
Sir, instead a peak at 0 degree, if we have some kind of null over there, then how we can define whether it is side lobes or a split beam?
There was some noise, so I'll try to repeat what you said. Let me know if if I heard something wrong. So you said if there is, let's draw a rectangular coordinate. For example, you're saying if we have some radiation pattern looking like this from 0 to pi, or we have some minor beams over here and this beams over here. Is this something you said if there are two uh, beams which reach 0 dB, right? If we have equal power in these two beams.
Gaussian, if you get a curve at 0 degree itself, but if you have a dip in the middle of that, so instead of a peak, if you get a small dip and then you have two peaks at the same time or same angle.
Oh,
So
okay, okay. It's just next to each other. In this plot,
yeah,
if we have a split over here, right?
yes, sir.
Um, so, uh, so it's definitely a split beam, and now you have two major lobes. So in the while going through this textbook, I've seen that the text says that you have usually you have one major lobe and then minor lobes. But right now, based on different works that we have seen, it's not necessary that you will have only one major lobe. You might have many major lobes. So this is an example of split beam. It could be either two beams, it could be next to each other, it could be at different angles, it could be spread apart. It could there could be multiple, like five, six beams or split beams of same magnitude in different directions. So it's fine. Yeah, what you're saying, this is the example of split beam. Um, uh, Lately, I've seen some people working on meta surfaces and antennas which have split beam functionality because they want to transmit, receive in different directions. So yes, this is a split beam. You're correct. Any follow up questions on that, or anybody else?
Sir, what is the major significance of 0 dB? It indicates the maximum radiation.
Okay. Yes. Good question. Why 0 dB is written over here? Where is my cursor? So when you can when we started plotting the radiation patterns, right? You must remember, we said we're normalizing the fields. Okay, so when we normalize, the maximum value that any term, any this electric field or magnetic field they will achieve is one, and one in logarithmic scale is 0 dB. So so 0 dB means you are achieving maximum power in that location. So if you have two beams, if you yeah, so if you have multiple positions, you'll like if you have two beams where you have reaching 0 dB, you are having uh, maximum power in those two directions, like that. So yes, uh, 0 dB means you are receiving maximum power at that point. Uh, Basically what you said was correct, so I tried to explain. uh, any follow-up questions on that? Were you able to follow why 0 dB is written?
Yes, sir.
Okay, yeah. So if there are no questions right now, we'll proceed to the antenna parameters, which are very important. If you are an academic or industry, you'll see them very frequently. This is the directivity, this is the gain, this is the radiation resistance and stuff. So a lot of terms thrown around. Um, so it's also very tough for me, at least, to keep track of all these terms. So I'll keep coming back to textbooks to go through them. So don't be overwhelmed if you see too many terms which sound very similar. Um, you can always open the internet and or textbook and go through them. But we'll see some of those terms now, because it is important that you understand. Because if you are reading a data sheet or some text on that, these terms will be used instead of explaining everything in text. They use these terms to specify those quantities. So in the previous examples, we had seen the radiation patterns of a Hertzian dipole. We have seen the radiation patterns for a more realistic dipole, which is probably lying on the axis like this. Okay. So the first term that we will discuss is the width of the main beam. So right now we are assuming that there is only one main beam. In this plot as well, you can see this particular thing is the main beam, and over here this is the main beam. Okay, so the radiation since these are examples of isotropic antennas. So you will have the main beam like this, like in this direction only. And these the radiation patterns are usually symmetric, so we just ignore the lower half. We just focus on the above half. Okay, and if they are not symmetric, then it would probably look something like this, like the radiation pattern. Okay, I've drawn very badly, so like if this is the circle in which you are plotting, and these are the axes, so your antenna could have radiation pattern looking like this. So in this case, this upper half would be the main beam, and then the side lobes are there. So okay, coming back to width of the main beam or simply beam width. So what is this beam width? I've written a lot of text over here. So the first way to define is the half power, or half power is minus 3 dB. I hope everybody follows this. 10 log base 10 half is equals to minus 3. Okay, so minus 3 dB is how we is the first way to define the main beam beam width. The three we also call it the 3 dB beam width. So what we do is we draw this plot over here. So 3 dB, okay, so 3 dB or half one power, and half power is like if, and since okay, so one thing we must notice. So we are plotting over here is the electric field, but we are saying half power. So half power is 1 by root 2 1 by root 2 value of the electric field, or 0.707. Okay, uh, so since this is normalized, this maximum power is at 1, you will get 0.707 value over here, which is 1 by root 2. And if you draw this line over here, wherever this uh, line intersects the plot, just take these values, drop them down to the axis, and you get phi1 and phi2 values. And the difference of this phi1 and phi2 values is your 3 dB beam width. Okay, or you can do this in the logarithmic plot as well. So what you do is you take the normalized electric intensity value, uh, take 20 log 10 of this thing, because this is electric field, we will take 20 log. If for power we take 10 log, so we are taking 20 log of this value. This will become 0. This is the minus 3 value. So at minus 3 you draw a line, drop down the places where the curve intersects. You get the phi 1 and phi 2 values. The difference of these will give the 3 dB beam width. So this is the 3 dB beam width. Lately, there is also something called as minus 10 dB beam width, and in that case, what you do is you search the value for minus 10 dB over here, and then draw the value, get the phi dash 1 and phi dash 2 values, and this difference will give you uh, the minus 10 dB beam width. Or there is another way to give the beam width is where you get the first nulls. So if you see this value over here at this line, we have the first null over in these two places. So if you take the difference, this delta phi also, this is also one of the ways to define the beam width. This is the first null beam width. Okay, so we saw the 3 dB beam width, 10 dB beam width, or the first null beam width. I'll just pause over here. We looked at the three different terms of three different ways of defining the beam width. If you have questions on this, I'll take them, or we'll just so you can read the slide, and if there are no questions, we'll move.
Sir, what is the significance of 10 dB or 3 dB kind of thing? Why?
Significance.
Yeah.
Yes, please continue.
Yeah. What is the significance? I wanted to know. So why we refer only 10 dB? Why can't we go for 12 dB or 15 dB kind of thing? So why only 10 dB?
Okay. So this is the significance is that it's more sort of a convention. Uh, like people wanted to quantify they wanted some sort of measurement for classifying it as beam width. So for the first null beam width, intuitively, if somebody asks you what is the beam width, so you will see the from where the beam starts and where the beam ends. So between those two nulls is where the total beam is there. So that's how we came up with the first null beam width. Now this for the 3 dB beam width is the 10 dB. I have not seen a lot of it being used at a lot of places. Um, so for the so I'll give you why 3, 10, and first null. So first null is the most basic way which you can define the beam. Between the two nulls, the entire beam is encapsulated. So the first null beam width is that's how we get it. For 3 dB is sometimes we refer to as and when we are designing devices, we want at least half of the power to reach uh, the device. Okay, so we are defining a new way in which you are saying that only the region or the beam width where you are at least receiving or you're transmitting the half power is the angle of your concern. So that's how we came up with the 3 dB. So there is okay. So first pause and answer this question. What is meant by the first null in the radiation pattern? Um, if you can see this point over here, I just highlighted in 11.4b these point first null. Since this is the normalized plot, you'll be able to see where the values where we're receiving the minimas. So this is the maxima. This is another maxima. This is another maxima. The x's are the maximas, and the zeros are the minimas. Okay, so these are the minimas. So the first minima that we achieve is the first null, starting from the main, like the main lobe or the pi by 2 value. We the first minima is the first null. This is the second null, and so on, and similarly in the other direction as well. So I hope I answered that question. And now coming back to, so we so now we understand what is the first null beam width is between the first nulls. So you can see this is the first null. These are the first nulls, and between that we have the entire beam encapsulated. But uh, for even if you are transmitting the power through an antenna, even for the first null, you if you say and you have a device, for example, which is placed in a position where okay, I'll probably draw this. So you have one antenna, a receiving device or an antenna of that device over here, and your radiating antenna is over here, and this is how your first beam is like, and this is the second beam, and these are the minor lobes. So your first null is over here, and this is the line I'm drawing to classify where the beam width is. So this is the first null beam width, right? This is the first null beam width we are getting from delta phi. But even if your device is inside the beam, because this is your angle which you have defined for it, so it is inside the beam, but it is in a direction where the power is very less. So this device over here will be receiving very less power, because it is, although it is inside the first null beam width, it is in a position where the power is very low. It would have received more power if it was probably over here in one of the minor lobes. So we came up with 3 dB beam width. So when you say that your device is between the 3 dB beam width, you're implying that this particular device is receiving at least half power, which is of the of the inside the main lobe of the maximum power that your device could send. It is receiving at least the half amount of power. That is the 3 dB. And minus 10 is, I think it's something I'm also not very familiar with, but I've seen in this text, so I've included. Minus 10 is somewhere we would say it is receiving at least 10% of power, if I'm doing the math correctly. So if your device is over here at the minus 10, it would probably mean it is receiving at least 10% or 1% of the power, something like that. Uh, um, I hope I was able to like explain this. If like, were you able to follow this? Do you have any follow-up questions? Also, Nikhil, if you were able to understand what the first null meant. Any follow-up questions, Hanuman?
Yes, sir. What I feel is that if you take a curve of spillover and illumination losses, so there the optimum value will be minus 10. Means the edge taper, what we look at, it will be around minus 10. So where it is the optimum value for your illumination as well as spillover losses. So that is the reason why probably people will be looking at 10 dB. That's what I feel.
That is a very good point. Yeah, so that could be one of the reasons. What we can do is, after the class, we could go online and check for the minus 10 thing, because this is something which I've also come across for the first time. If you go through Balanas, over there, first null and 3 dB are the only beam width discussed. Uh, so that could be, but yeah, so first null is, and first null encapsulates the entire beam. 3 dB encapsulates the uh, angle in between the, like, the angle which encompasses at least the half power. So these two are the important ones from the textbook point of view. So there's another question: is half power always 3 dB constant? I'm not sure if what the question meant. So half power is what, as I said, 10 log base 10 of 0.5, or half. So if you solve this, this is 10 log 10 to power minus 1. This comes outside, so this becomes minus 10 log 10 to log 2 base 10 is 0. 0.301, I think. So this is minus 10 into 0.3 something. So 30 some 1 probably. So this becomes minus 3 dB. So this is how we are saying that we have minus 3 dB thing. If I was able to, yeah, good. And any other question? So to add to that, half power is minus 3 dB only if your maximum power is 0 dB. And why is our maximum power 0 dB? Because we have normalized it. So again, focusing on the term normalized. So for normalized terms, the maximum magnitude is 1, which corresponds to 0. Okay, so if there are no questions for the questions on this, we'll move to the next term, which is the side lobe levels. So when I was going through this particular text, I found that the text mostly implied that the side lobes are problems. I recently have seen some works in which side lobes may not be problems if you can use them in certain way, or if you have, as I think Hanumant or somebody had said, if they are split beams or if you have more than one beams. So what is exactly a side lobe? So I personally define any lobe which I don't want as a side lobe. So don't write this answer in an exam citing me, but to me anything which to any lobe that you don't want is probably a side lobe, and that is a problem. And what we do is we try to minimize the amount of power in those side lobes, and everything else is your major lobe, and you try to maximize the power in that. So you want the directions in which you want to send the power, you want to maximize that, and the directions in which you don't want power, you want to minimize that. There could also another reason which like why you want to reduce the amount of power in the side lobe is that you might have a antenna over here which is radiating in these two directions, and then you have a side lobe over here, and then there is another device of your own interest, and it is also communicating in some directions like this. And what will happen is, if these two, and you don't want these two antennas, although they're in close proximity, to interact, but what could happen is these antennas will interact if they have minor lobes in these directions. And look, maybe I can draw a better picture. So for example, if you have two antennas very close proximity, and one is your transmitter, one is your receiver, and your transmitter radiates in this direction, your receiver radiates in this direction, and this is how you designed your antennas, so that they uh, transmit receive at a particular angle, and they and you have to place them in close proximity because the lobes are in different directions, but they will have smaller lobes. And in your task is to minimize the back radiation or the lobe which is towards the other antenna. So if they even have smaller lobes, but if there is enough power in between them, they will interact. And to reduce that, you want these lobes, the power in these to be very small so that they do not interact. So these are the side lobes, the lobes which are of not of interest. There are the side lobes, and side lobe level is the amount of the magnitude of power which is in them. So this 0.39 magnitude or minus 8.2 magnitude. These are the side lobe levels. So side lobes of a directive non-isotropic pattern. So this is a directive pattern, and this is a isotropic pattern. So when we are talking about these, they should have low levels as possible. Okay. There's another question. What happens if two back lobes of two different antennas overlap? So okay. So these radiation patterns is something which we are drawing. So there is no so the overlap is not exactly so by overlap over here, when I made a figure where the lobes overlapped, it was just a way of emphasizing that there's enough interaction going on between those two antennas, that the power between them is enough for them to communicate. So that is what I implied when I overlapped the two lobes. In reality, the this is more of a continuous thing. So there is still power in that direction, but it could be very low, which implies a very small side lobe. Uh, and then you could say that they do not overlap. So don't take that very literally. This is a very figurative way of showing. So coming to your question, if what if they overlap, it means when we are saying overlap, we are saying that there is enough power between in that direction, like is being transmitted from those two antennas in those direction, that they can communicate. Now, if you intend for those antennas to communicate, it is a good thing. If you intend those antennas not to communicate, but the side lobes in those directions are significantly high, those two antennas will communicate and will and if you don't want to communicate, this probably means that you're corrupting the signals if they are working at the this assuming that they are working at the same frequencies. So what will happen is you for example okay, let's take this example. Let's say this over here, they're overlapping, right? But this is but this and for this receiver, this is not the intended transmitter. Its intended transmitter was somewhere here. Okay, then we had a transmitter which was the and this we have receiver, and this is the intended transmitter and the receiver system, and then this is another transmitter, and we did not intend to receive from this transmitter, but this transmitter is also sending signals over here. So now you are receiving signals from two sources, and only one of them is desired. So this will bring in problems because you are receive whatever you receive from the antennas, they are basically voltages. So they it will create problems later on for signal processing. So this basically it's not desirable, which could cause problems. I hope I was able to make that clear. Nikhil, do you have any follow-up questions on that? You can type that in chat. Meanwhile, we can continue with further discussions on side lobes. So generally, the levels of the distant side lobes are lower than the levels of those the near main beam. So this is an observation, more like an observation that the side lobes which are near to the main beam, they are usually higher and they become lower in as we move away from the main beam. But this will not hold up if you have more than one main beams. Then it could be very random. But usually true if you are making some non-isotropic or directive antenna, the side lobes next to the main beam will be usually higher, and we try to suppress them because we only want uh, ha like high power or yeah, inside the main beam. When one talks about the side lobe level of an antenna pattern, one usually refers to the first, the nearest, and the highest side lobe. So, yeah, so this term is important in the sense if you are being given a direction that you want a high, like a very directive antenna with a certain amount of radiation in one direction, and then you will be said that the side lobe level should be below 20 dB or something. So when they say that the side lobe level should be below 20 dB, they mean they usually mean the immediate side lobe, which is next to the main beam. Because if there might be some applications in which this is the beam which you want the receiver to have, but if the side lobe is significantly high, it will create problems for this. I'm not sure exactly how those problems would be, but it is not desirable. This is more towards, I think somebody has worked on radars and stuff. I think over there they probably understand better if how the side lobes create problems. But yeah, as an antenna designer, you will be asked to reduce the side lobe levels. It could be as high as minus 40 decibels. So you have to make sure your main beam and your side lobe levels are below minus 40 dB. If you achieve this, this is a pretty good standard to like maintain. Okay, so in the last point, it said, I was saying, in the practical applications, the locations of the side lobes are also of importance. So there could be a case in which, like, you have your main beam over here, and then you have a side lobe level. You were said that you were told that you want it below minus 40 dB, but you could but you still have side lobe levels which are greater than minus 40 dB, but they are in a direction which is not relevant. For example, if this is a side lobe over here, which is greater than minus 40 dB, but it is in a direction which is not relevant. So you could just be satisfied with this direction, and like, as you for sure know that in this direction you probably won't have any devices placed. Only have devices in this direction. So it's fine. You can just ignore the back lobes and the side lobes at the rear side of your transmitter and be okay with it because it won't affect your performance. So we discussed the side lobes. If, have any questions on what we discussed? I'll pause over here, let you read the slide and the points. If you have questions, you can ask them. Else, we'll move to the next topic, directivity. Okay, yeah, so we'll proceed now. The third important term is the directivity, and from directivity we'll do some further examples and derivations, and then we'll end the class. So directivity, it's one of the most important terms, and from directivity will come gain and other terms as well. So the beam width of an antenna pattern specifies the sharpness of the main beam. So we have seen that how sharp this is more isotropic, this is more direct, this is more sharp, and we can also say this is more directive, but we need to quantify how directive. But and also it does not provide any other information about the like the antenna properties, for example the efficiency and stuff. So we must quantify those things as well, but from the pattern we are getting a with a pretty much good idea about in which direction should our receiver placement be, how the antenna is radiating spatially. So those things are correct, but we need some quantified values now. uh, there is there is an example in the book which says the side lobes may be very high, which is an undesirable feature. So we have discussed beam width. Now we know we have this last slide we saw side lobe levels, and this they are quantified by these values. And now a commonly used parameter to measure the overall ability of the antenna to direct radiated power in a given direction is called directive gain, or the directivity in short. And now this directive gain is defined in terms of radiation intensity. So this is more the sort of recursive thing. So if you have directivity over here, which is in terms of radiation intensity now. So now we must define radiation intensity, and then we'll go back to directivity. So radiation intensity is the time average power per unit solid angle. Okay, too many terms at once. we have to break them down. Time, average, power. So there is a device which is radiating in all directions, and it's, for example, it starts radiating from T0 time to T1 time at T2 time at, so at different so it is radiating through with reaching with time, and it is radiating some power value P0, P1, P2. Okay, so and this, although these values will be like very similar to each other, but anyways, so we at different time instants, what we can do is we can measure the amount of power which is being radiated by this antenna, and then we can take an average of how much power is it is radiating uh, at any time, and at but at an instant how much power it radiates. So we will get the time average power. And now since this antenna is radiating in a 3D space, it is radiating in a 3D space. So what we will do is we'll at a we at a particular in a we will try to calculate per unit solid angle. So uh, I hope everybody follows what a solid angle is. So if you have a sphere, and if you make make this per unit area, so this particular this angle which projects for a particular slice of the surface area is the solid angle. I hope I was able to convey that. So per unit solid angle, the amount of power which is radiated. So okay, so I'll put it like this. So you have an antenna which is radiating, and if you take the and if you consider a sphere around the antenna, so at on that sphere, it is some amount of power is incident at all time. So at all time, we will take an average of the power which is incident. So we'll get an average power which is incident throughout this sphere. And throughout this sphere, for each solid angle, for one solid angle, we'll calculate how much power is being emitted on through on this sphere. So we will get a term called the radiation intensity of how much power, how much by how much intensity the power the radiation is happening at that particular point on that sphere. I hope I was able to make that clear. So that is radiation intensity. Now, in terms of radiation intensity, in the next slide will define the directive gain. So I'll just pause here, let you read the sentence. If you let me know if you were not able to follow that. Maybe I'll try phrasing other sentences to make sense. Okay. Uh, there are no questions. I'll assume that radiation intensity's definition is clear. So it is the time average power per unit solid angle. Its SI unit is watt per steradian. Uh, might be a question in some exam, but so interesting unit. Okay, so since there are r square meters of spherical, so we're now writing the expression for radiation intensity. So so considering there is an that there are r square meters of spherical surface area for each unit solid angle. So there is some sphere, and then there is this patch over here whose area is r square for one particular solid angle. Okay, this is probably derived like this. Um, so the total surface area for a sphere is, I guess, 4 pi r square. Please correct me if I'm wrong. and the total solid angle for one particular sphere is 4 pi. So if you calculate the for each solid angle how much area you'll get is r square, because this 4 pi's will cancel and you'll get r square. So there are r square meters of spherical surface area for each solid angle. The radiation intensity U equals r square times the time average power per unit area. So the previous slide we discussed. Okay, there is a question. To have more directivity, is the beam width should be less? Um, through this answer, this question will be answered in the coming slides. If I say yes now, it might not make a it might make sense or not make sense. Answer is yes. So to have more directivity, the beam width should be less, and it will become clear as we discuss the next few slides, because when we are uh, plotting the gain or yeah, and the directivity term itself is related to how narrow is your beam width and like those. So yes, so to have a more directive antenna, your beam width should be less. And it also comes from the fact that the Hertzian dipole is an isotropic which has a 90-degree beam width, and a more directive antenna is a regular dipole. The other figure that we saw where the beam width was much narrower, so we had uh, it was more directive. But directivity over here quantifies the amount of power which is in that one direction, which will become clear when we. So I'll say it in a gist right now. So, so the antenna can radiate some X amount of power. We're fixing that. So this X could be radiated in all directions, or what we can do is reduce the X in other directions and make it higher in one direction. So this is some sort of thing which I understand might not be correct, but might not be the best way to say, but this is what. So you can either distribute the entire power in throughout the directions, or you can concentrate it in one direction. Maybe I'll come back with a better answer to this in the next class. But let's focus on this thing now. Nikhil, maybe I'll come with a better answer to this. I will say yes to your question, but I don't really have a very good explanation for that. So I'll look it up and share it with you. Okay, coming back to the radiation intensity. So we have r square meters of spherical surface for each unit solid angle, and the radiation intensity equals r square times the time average power per unit area. And this time average power per unit area could be the can be written as the magnitude of the time average Poynting vector PAV. So this is your time average power, and this and your radiation intensity, which is given by U, a very unusual notation. But remember, when if you see U, it is radiation intensity, and then your Poynting vector gives you the time average power. So the time average power into the so solid angle gives you the radiation intensity. Okay, so this is the expression for the radiation intensity. Now the total time average power is given as here. So we'll integrate uh, the time average power in with the total surface area, and this. Okay, so this ds will become, so yeah. So yeah, d omega, which is the solid for the solid angle, is written as Yes. So there is some notation thing going on here. So ds is the total surface area, right? Yeah. Um, how do we write this? I just forgot how to write. I think it is sine r square sine theta d theta d phi. Yeah. So ds is written as r square sine theta d. So this is theta and d phi. And if you write this replace this over here, your PAV into r square um, will become PAV into r square will become u, and your d omega is sine theta d theta d phi. Were you able to follow this? We wrote ds as r square sine theta d theta d phi. And now PAV into r square becomes u, and sine theta d phi becomes d omega. This is the differential solid angle. Okay, so this is the total radiated power. Okay, so the directive gain G given by GD, which is a function of theta and phi of a antenna pattern, is the ratio of the radiation intensity in that direction, in the direction to the average radiation intensity. So okay, so your question's answer is here somewhere. So the directive gain of an antenna pattern is the ratio of the radiation intensity in that direction. So when we were plotting the radiation patterns like this, so the it gave the radiation intensity at each point. Okay, so we okay, so and uh, what we do is if we have this total power as which is distributed along all the directions, and we will take the ratio, so we will get the directivity in that direction. So if okay, maybe let's do the expressions first, and then we'll try to draw figures and understand. So as I said, it is the ratio of the radiation intensity in that direction. So radiation intensity in that direction by the total average radiation intensity, which is this is the total average power into the average power divided by the total surface total angle, which is yeah. To the average radiation intensity. Okay, so the average radiation intensity will be you have u over here, you have r square into total power divided by 4 pi r square. 4 pi r square is the total surface area, and this is the this is the your radiation intensity in that direction. So if you cancel this, you will end up with PR by 4 pi, which is over here. So, and this is your radiation density in that direction. You can also write this as integral of surface integral of u d phi. So this is, you can also write this PR over here, and then 4 pi is on taken to the numerator. So this is the expression of directive gain. And now what the sentence says. The directive gain of an antenna pattern is the ratio of the radiation intensity in that direction to the average radiation intensity. If your antenna was, as I said, if your antenna had certain amount of power, and if it radiated that power equally in all direction, you will get an isotropic pattern. And if the same and but your antenna now but your antenna radiates in a very weird way like this. So in this direction you have less directivity, in this direction you have less directivity, and in this direction you have more directivity. But when we say directivity, we just ignore these areas and we just only focus on the main beam, and we give the directivity of this. So if you are reducing power in the other directions, it implies you are focusing them in one direction, is somewhat the sentence means. So hence, if you want a more directive antenna, it probably means it will be less isotropic, which means it will have a narrower beam width. So I'll pause here because just half of the slide, in the half of the slide, we had a lot of information. Although I have scribbled a lot, it's still readable, I guess. Please let me know if you have questions on this, and then we'll continue. Okay, I hope everybody was able to read the slide. We'll continue. Obviously, the directive gain of an isotropic or omnidirectional antenna, an antenna that radiates uniformly in all direction, is unity, which is unity means 1 or 0 dB, and at times you will be told that you need at least 7 dB gain. So this is bad in those cases. However, an isotropic antenna does not exist in practice. Okay, so there are antennas, okay, and do not exist in practice. So Hudson dipole, which is an isotropic antenna, but it is like in an ideal situation where you have a very small radiating structure. But you could make antennas which could mimic isotropic antennas, but they won't be ideally isotropic. And omnidirectional antennas are just fictitious. They don't exist. Even in um, you cannot have a design which will be omnidirectional. Uh, Even have a mathematical model for that. Okay, so the maximum directive gain of an antenna is called the directivity of the antenna. So you will have directive gain in different directions, and then you will have a directivity, which is the maximum directive gain of the antenna. It is the ratio of the maximum radiation intensity to the average radiation intensity, usually noted by D. So in one of the directions, you will have the maximum. So you will write that, and then you have the radiation intensity, and which is U average, which is given by PR by 4 pi. This is U average. We calculated it over here, PR by 4 pi, and this is dimensionless. In terms of the electric field intensity, because everything over here was power and stuff, so we can write the directivity in terms of electric field intensity, and for that we'll be substituting the Umax value and PR values, and upon doing that, we will get this. So in this, we have we have normalized, we have cancelled out common terms. Okay, so this is what we will end up with. Maybe try deriving this solution. You can find it in CA Balanis. Okay, so I'll again pause here for a minute or so and then we'll proceed. We started a little late, so we might overshoot the 5:30 time. We only have a few more slides to go. We'll do that and then we'll end the class. Okay, so maybe we'll move a little faster now so that we can uh, end the class earlier because everybody is might be tired already. Directivity is frequently expressed in decibels. So yeah, I was saying dB, but I did not realize we were still doing it in magnitudes. So we usually discuss, we'll take them in logarithmic scale to it's a sort of a norm. So we'll solve a question now where we intend to find the directive gain and the directivity of a Hertzian dipole. In the previous slide, we already did some question we have done the electric field intensities also. So we'll use that. So for a Hertzian dipole, the magnitude of the time average Poynting vector. So Poynting vector is given by half of real part of electric field cross magnetic fields conjugate of the magnetic field, which is given by this expression. This comes from your electromagnetic theory. And then from the expressions which we have derived in the previous class, we'll substitute the H value over here, the electric field value over here, we'll multiply them, and uh, this is we'll multiply r square to that as well, r square PAV, and so and use that also. So we'll end up with this expression, the radiation intensity. Okay, so this is just substituting stuff and then solving. We end up with the radiation intensity. And now the directive gain we derived in the previous slide is given as 4 pi u divided by uh, surface integral of u. From this expression, we have substituted u over here. 4 pi is this thing, right? This is the coefficients. They are gone because in the numerator also you have u and denominator also have u, and the coefficients are like independent of the integral term, so they are cancelled. So you just end up with 4 pi, which is from here, and the sine square theta over here, and then and the integral you have sine square theta over here, and then d phi d omega is expanded to sine theta d theta d phi. So you end up with this integral. Now this is a high school problem sort of thing. Um, we just need to integrate, and we end up with this directive gain pattern. So this is 3 by 2 sine square theta. Now, even if we have the expression for this thing, it's very difficult to visualize how the radiation pattern would the directive gain pattern would look like. But sine square, this is sine theta, and sine square theta becomes something like this, and then so your pattern would become something like this probably for the directive gain. Okay, so the directivity is maximum value of GD, and the maximum value of this particular term is 3 by 2 because sine square theta can go to a maximum value of 1. Um, so, um, so this becomes 1.5. We have 1.5 directivity, and expressing it in the logarithmic scale, 110 log 10, 1.5 becomes 1.76 dB. So this is the directivity of a Hertzian dipole. Okay, so I'll pause at the this example and let you go through the steps. Let me know if you have any queries on this, else we'll move to the remaining slides.
Sir, I have one question.
Yes, please tell me.
So directivity means maximum radiation. And what is the major difference between the directivity and the directive gain?
Okay, good question. Directive gain can be in all directions. Directivity is the maximum value of the directive gain. So the maximum value of directive gain will be in the direction where there is the major lobe.
Hmm.
So if you had some antenna which was radiation pattern look like this. Over here you have less directive gain. Over here you have less directive gains. So gain you can find out in all directions. So you can say directive gain or just gain also, I think. So there are different types of gain. So we refrain from just saying gain. So in all directions there will be some value of directive gain, and the, the direction where it is maximum is the directivity. Uh, was it clear?
Yes, sir.
Any follow-up questions? Okay, so we still have a few slides, two, three, I think, to go. We'll quickly do that. We note that the beam width, the side lobe levels, the directive gain are parameters of antenna pattern. They do not convey information about the efficiency or the input impedance of the antenna. So we'll now focus on efficiency and the input impedance of the antenna. A measure of the antenna efficiency is the power gain. So we saw directive gain. Um, okay, so we saw directive gain. Now there is something called power gain. Okay, so this is another type of gain which will give you the idea of which will give us the idea of antenna efficiency. Now, power gain or simply gain. Okay, sorry. In the previous, I was saying gain. So, power gain is the more realistic gain that we usually talk about. So, there is one thing as directivity and there is one thing as gain. The directivity gives you some sort of idea where the gain would be maximum or where it is radiating maximum. But gain encapsulates more terms. For example, the efficiency or the mismatch losses and all those things are encapsulated in the power gain or simply the gain. So this is given by GP. Directive gain was given by GD. The directive gain, the power gain of an antenna referred to as an isotopic source is the ratio of its maximum radiation intensity to the radiation intensity of a lossless isotropic source with same power input. Okay, so it is very similar, but over here we are using lossless isotropic source as the reference. Okay, so let's write the expression. This was the expression for the directive gain. Okay, so this is the expression for directive gain. Uh, the directive gain over here, you see, this is based on the radiated power. So the amount of power which is being radiated to the total amount to the amount of power in that direction. Okay, but for the but when you are writing radiated power, we are missing out the ohmic power losses within the structure. So there are some losses as well. So basically, you want the gain would be the amount of power which you put in the antenna, and then the amount of the power that you're receiving or the like at different points. So what we do is we replace the radiated power over here with the incident power, and then we get the this power gain or this gain. So incident power will be equal to the radiated power plus the power which was lost. So this becomes the incident power, and the expression for the power gain is then 4 pi u max by the incident power instead of the radiated power. And the ratio of the gain to directivity is given as the efficiency. So this is the uh, gain, and this is the directivity, and this ratio will be equal to the radiated power with the incident power, which makes sense. So this is the efficiency, the how much power is being radiated, how much power being is the incident, and there must be some power which is being lost. So for a well constructed antenna, the efficiency would be 100%. Another useful measure of the amount of power radiated by an antenna is its radiation resistance. This is a fictitious term, but very used like often uh, among antenna designers. The radiation resistance of an antenna is the value of a hypothetical resistance that would dissipate an amount of power equal to the radiated power when the current in the resistance is equal to maximum current along the antenna. So basically, when you have the maximum current and you want to radiate up the certain PR amount of power, you will have some you can find out some resistance value by and that is the radiation resistance for that antenna. So a high radiation resistance is desirable property because in that case, the power is given by I square R, right? So if you have a higher R, um, you will have a higher power, like the radiated power. I'll pause over here. So we have, I think, one more example to solve, and then we'll end the class. Any questions on this? Okay. So this was pretty straightforward that we had we had a directive gain, and then which had a radiated power. We replaced the radiated power with the incident power, which gave us the power gain, and then we took the ratio of the power gain and the directivity and got the value for efficiency. And we looked at a fictitious term called radiation resistance. So let's solve this example and then we can end today's class. So over here, the problem is to find the radiation resistance of Hertzian dipole. And to solve this, we'll end up calculating a whole lot of terms, which is good for us to see how to solve problems or how to calculate these parameters. So assuming there are no ohmic losses for this particular, in this case, the time average power for a Hertzian dipole is given like this. So this is basically we are taking average of the Poynting vector thing. You must remember PAV was something half E cross H, and we took the real part, and then U is equals to R square PAV, and then this PR was is equals to integral of U d omega. So this substituted inside this, and then this substituted inside this is something we end up like this, the radiated power. And now radiated power is given in terms of electric field and magnetic field. And we had solved for Hertzian dipole, electric field and magnetic field values. We'll substitute these over here and then solve. So this is just a lot of steps, but you will end up with, after integration, we'll end up with uh, PR is equals to this term over here. Okay. So essentially, in the far field, we have done approximations. This e power terms are gone. We have the this R and stuff are also. So these bracket terms were simplified for far field, and then we ended up with only sine theta from for e theta and h phi. So we had sine cube inside the integral, and to solve this is again a high school problem. So you can solve that, and you'll end up with this expression. Oh, and over here, some things were simplified. For example, instead of eta naught, we have substituted 120 pi, which is, we know the intrinsic impedance of free space. And 2 pi by lambda was substituted for beta. We had beta, we have substituted 2 pi by lambda, and we ended up with this expression. So this is the radiated power of the Hertzian dipole. Okay, now for the Hertzian dipole, we have if we have no losses, we can write radiated power as I square r by 2 over here. So we can write I square r by 2, and then this I square 2 things will cancel, and we get r r as 80 pi square by dl upon lambda whole square. So I've calculated the radiation resistance. So I'll pause here if you like to let you read these steps, um, and the next few slides will wind up. Okay, so moving on. So, so this was the expression that we got. So for a very small value of lambda. So this is a Hertzian dipole, right? So lambda, this dl length is very small. So for a small 0.01 times lambda value, the radiation resistance is only about 0.08 omega. But we said that we need a higher radiation resistance for a good radiator. So a short dipole antenna is a poor radiator. But this does not imply a longer will dipole antenna will be better, because the expression because we assume that the current distribution because we assume that the current distribution across the dipole is same while uh, calculating the radiation resistance. The electric field and magnetic field, when we were calculating, we assume that there is equal current distribution. So we cannot directly say that a longer dipole is better without actually calculating that, because this expression dl, which it should be much less than lambda for the 1144 to hold true. This expression holds only if the electric field and magnetic field expression that we use from the Hertzian dipole are correct, and they're correct only if we assume they're only correct when the current distribution along the dipole is constant. So the radiation resistance may be quite different from the real part of the input impedance, because uh, the real part of the input impedance includes ohmic losses in the antenna structure itself. So this will come across this later, but we have to ensure that we do not confuse between radiation resistance and the input impedance. These are two different terms. So the input impedance of a short dipole antenna will have real and imaginary parts, and usually and it has capacitive reactance, which makes the matching feed power difficult. So this is also something, a problem which we'll see later. But radiation resistance is not same as input impedance. We have to be very clear with that. Okay, so this is sort of that example, but again continued. So now what we have to do is we have to find the radiation efficiency of the isolated Hertzian dipole made of a metal wire whose dimensions and conductivity are given. And in the previous slides, we have derived these expressions. We have the efficiency expression, power expressions, and the radiation resistance expression. So I'll go through the steps and then I'll end the class. If you have questions on this, so you can come back to me later on the next class also. So we have let I be the amplitude of the current in the wire dipole with loss resistance RL. So the power which is lost is given as half I square RL, which is the loss resistance. Similarly, the radiated power is given as half into the radiated resistance. Um, Radiation resistance, and then from 1139, which is this expression, and 41, which is this expression. The efficiency is written as um, radiated power by the total power. The total power, that is the radiated power by the incident power. Incident power is the radiated power plus losses, and then if we substitute this 11, 45, 46 and stuff, so we end up with radiated resistance upon radiated resistance plus lost resistance, and we can simplify it to bring it like this: 1 upon 1 plus RL by RR. And then when RR has to be the RR was found in the previous slide, which was previous example, which is equal to this. And then we need to calculate now the loss resistance. The loss resistance can be given as so if you remember, resistance is equals to rho lambda by surface area. So something like that, surface resistance into the length of the dipole and the cross section of the dipole. Okay, so those and the surface, this conductivity or surface resistance is given as root over pi f mu naught by sigma. So this is previous knowledge. So we will substitute that and this. So yeah, so the radiation efficiency is given as eta r, and the eta r was 1 upon 1 plus RL by RR. So RL, as we have calculated over here from these two expressions, and RR is given over here. So we end up with this is the expression for radiation efficiency. Now there now we need to calculate the final value. We were given that the cross section, the radius was equals to 1.8 mm, the length was 2 meters, the frequency was 15 megahertz, and the conductivity is given. So we just substitute that. Um, so we calculate the lambda, we calculate the RS value from the known values, we calculate the RL values, we calculate the RR values. We have got these values, and then we substitute them in this expression, and we get the efficiency as 58%, which is very low. So Hudson dipoles, they are not very good, as seen from the radiation resistance and the efficiency. And this 1150 expression, where is the 1150? Yeah, the 1150 expression shows that a smaller value of A by lambda and DL by lambda. This, if these are smaller, we have lower radiation efficiency. Okay, so we took a lot of time today. We started late, so I'll stop here. In the next class, we'll look at thin linear antennas, half wave dipole, and effective antenna length. I'll share these slides now, and if you have questions, we can discuss them in the next class or in the WhatsApp group. If you have any questions related to today's class, or I'll pause for few minutes. If you have any important questions that you want to discuss now, we can do that, or we can take them to the WhatsApp group. And since we overshot the time, I won't keep you long here. Okay. So no questions. We'll end for now. Thanks for joining. I'll try to take a few classes in the coming week so that we can cover up the time which we lost. Okay. Thanks again for joining.